Okay, we're diving straight in today. There's this massive, really comprehensive piece on diffusion models out now. Seriously, it pulls together years of research.
Yeah, it's basically the definitive guide for where generative AI is right now. If you're in ML, this is the reference.
Absolutely. And we've kind of boiled it down to three, let's say, core takeaways that really define everything.
Exactly, three big ideas.
First insight, unification. Turns out those different approaches we used to talk about, DDPM, score-based models, even flow matching, they're not really separate.
Right. They all fundamentally map back to the same continuous time math. It's like finding out different roads all lead to the same place. One core problem, reversing noise.
Second, control. Generation isn't just random anymore, it's highly steerable. We've got much smarter ways than the old methods. Think classifier-free guidance, that's standard now.
And even more, alignment. Getting models to follow human preferences. We're now skipping the whole messy reinforcement learning thing with direct methods. Diffusion DPO is a big one there. Much simpler.
And the third big one, speed. That old problem of waiting ages for a sample, pretty much solved.
Yeah, dead in the water. We have these really clever numerical solvers now. Think high-quality images in like 10, 15 steps, or even better.
You train models that learn to jump straight from noise to the final image, almost instant generation with things like consistency models.
So unification, control, and speed, those are the pillars. Everything major builds on these.
Okay, let's unpack that first one, the unification, because that really sets the stage. For a while, it felt like there were these totally separate camps. We had the variational view, DDPM.
Right, the original denoising diffusion probabilistic models. The whole framing there was Bayesian, maximizing the evidence lower bound, the ELBO. You had this fixed process adding noise.
Slowly adding noise.
Yes, slowly fixed. And then the model's job was to learn the reverse, how to denoise it step by step.
But it was so slow in practice. What was the hang-up with that variational approach?
Well, it was baked into the math, really. To keep the reverse steps manageable, like mathematically close to a simple Gaussian transition, you had to take tiny steps, hundreds, often thousands.
So big steps would break the assumptions.
Exactly. The process wouldn't look Gaussian anymore, and the model would just fail at reversing it accurately. So fundamentally, you were locked into this Odella complexity. Many, many steps. Very slow.
Okay, then parallel to that, you had the score-based approach emerging. NCSNs, noise-conditional score networks. Different angle.
Totally different angle. Came more from the energy-based model world. The focus shifted to learning the score function. That's the gradient of the log probability density of the data.
So basically learning which way to nudge points to make them look more like real data.
Precisely. And the clever trick was denoising score matching, DSM. That let them estimate this score without ever needing to compute two horrible things from earlier EBMs. That intractable normalizing constant, the partition function, zero always. And also avoiding this huge, computationally expensive Jacobian trace calculation. DSM made score estimation practical for high-dimensional data like images.
So we had DDPM, slow but principled denoising, and NCSN, faster gradient estimation. The unification moment, the continuous view, that's where it all clicks together.
Absolutely. That's the core insight from the more recent theory, especially the work on Score SDEs. Realizing you can view this whole noise adding and noise removing process not as discrete steps, but as a continuous evolution governed by stochastic differential equations.
And the reverse process, getting samples back.
That becomes solving a differential equation. Usually the deterministic version, the probability flow ordinary differential equation, or PFODE.
What's the proof? How do we know these seemingly different things? DDPM steps, score matching, ODE solving are equivalent.
It comes down to a fundamental physics principle, actually. Mass conservation, the Fokker-Planck equation. It describes how the probability distribution evolves over time, and it holds true whether you're looking at the forward SDE adding noise, the reverse SDE removing it, or the deterministic PFODE flow.
So the same underlying law governs all of them. They have to be solving the same problem.
Exactly. It's a really elegant unification.
That's huge, because it means you have choices. The paper talks about these 4 different things models can predict. The noise, the clean data, the score, or this thing called velocity. They're equivalent.
Yes, completely equivalent algebraically. You can convert between predicting noise, epsilon predicting the original data, the score, using simple formulas. They're just different parameterizations of the same underlying vector field that drives the generation.
So why pick one over the other if they're the same math?
Purely practical reasons, usually. Sometimes one parameterization leads to slightly more stable numerical integration when you solve the ODE. Other times, one might make the training loss behave a bit better. But it's not a fundamental difference in what the model is learning. It gives engineers flexibility.
Okay, perfect segue. If we have this unified generator, the next step is telling it what to generate. Controllability.
Right, guidance. The basic idea is you want to sample from a conditional distribution, PTXEHC, where causes is your condition, like text. You do this by taking the model's natural inclination, the unconditional score, and sort of nudging it, tilting it, using information from the condition.
The first way people did this was classifier guidance, CG. How did that work?
CG was clever, but bit clunky. You needed to train a separate neural network, a classifier, that could predict the condition given the noisy data, $6 at any time.
So 2 models.
2 big models. The classifier gives you the gradient you need, 1 of Black's log, PCXTT. You then scale that gradient by some weight, omega, and literally add it to the unconditional score prediction from your main diffusion model. It works, but yeah, training and managing 2 models is inefficient.
Which brings us to Classifier-Free Guidance, CFG. This is everywhere now. Why is it so much better?
The efficiency gain is massive. With CFG, you train just 1 model to do both jobs. During training, you sometimes give it the condition, like a text prompt, and sometimes you give it a null condition, like an empty string, represented by empty set.
So it learns both conditional and unconditional generation paths.
Exactly. Then, at inference time, you get both the conditional prediction and the unconditional one from the same model with just 2 forward passes. You find the direction between them and extrapolate outwards. It gives you that steered generation without needing a whole separate classifier. Huge win.
Okay, CFG handles steering based on prompts. But then there's the deeper alignment problem, making the model generate things that match complex human preferences, aesthetics, safety rules, stuff that's hard to write down in a prompt.
Yeah, that's traditionally where RLHF came and reinforcement learning from human feedback.
Yeah.
But it's notoriously complex.
How so?
It's usually a multi-stage beast. First, you collect human preferences on generated outputs. Then you train another model, a reward model, to try and replicate those preferences. Then you use complex and often unstable reinforcement learning algorithms like PPO to fine-tune your generative model using that reward signal. It takes a long time, lots of data, and can easily go off the rails.
Okay, so what's the alternative? You mentioned diffusion DPO, direct preference optimization. How does that bypass the RL headache?
It's a much more direct route. DPO and its diffusion variant looks directly at the preference pairs, the output humans liked and the one they didn't.
Yep.
It formulates a loss function that directly optimizes the main generative model.
Without needing a reward model in the middle.
Exactly. No explicit reward model. The loss function is derived in a way that it effectively encourages the model to be more accurate in its prediction, in terms of MSE usually, for the preferred sample compared to the rejected sample, relative to some fixed reference model policy.
So it's about relative accuracy between the liked and disliked samples.
Precisely. It nudges the model towards preferred outputs while staying anchored to the stable reference model, avoiding all the instability of optimizing a separate reward signal with RL. It's simpler, faster, and often more stable. Big improvement for alignment.
That really doesn't like a shortcut. Okay, brings us neatly to part 3, speed. The elephant in the room for a long time. Even with perfect control, solving that ODE step by step takes time.
Absolutely. You want to generate fast, which means taking bigger steps, larger dollars. But bigger steps mean more error when you approximate that ODE integral. So the race was on, how to get high fidelity with very few steps.
The first approach was better math, right? Training free solvers.
Yeah.
DDIM was an early one.
DDIM was a key step. It gave us deterministic outputs, which was great. We now understand the DDIM update rule is essentially a simple first-order Euler method applied to a particular way of writing the PFODE, the exponential integrator form. But still, first order means you need quite a few steps for good quality.
So to really cut down steps, we needed higher order methods, like the DPM solver.
Exactly. The DPM solver family was a big leap. They use clever tricks like reparameterizing time, often using the log signal-to-noise ratio, lambda. This simplifies the structure of the OD, making it possible to apply higher-order numerical methods, K2 or more, accurately, drastically reducing the number of steps needed.
And the state-of-the-art there, DPM Solver v3, tackles this problem called stiffness. What's that about?
Stiffness happens when different parts of your system change at vastly different speeds. It makes standard ODE solvers unstable unless you take tiny steps. DPM Solver v3 gets around this really elegantly. It splits the model's predicted velocity field into a nice linear part and a more complicated nonlinear part. And here's the trick. It figures out the best possible linear part to use at each time step by solving a tiny, super fast least squares optimization problem. This customizes the solver on the fly to handle the stiffness.
What does that mean for us, practically?
It means you get rock-solid stability even with very large time steps. We're talking high-fidelity image generation in maybe 10 to 15 modeled evaluations, almost real-time, without retraining anything.
Incredible. But then there's the other path to speed, training-based.
Yeah.
Forget solving the ODE iteratively, just teach the model the answer directly.
This is where consistency models CM really broke new ground. The goal here is radical. Train a Model 5 alerts and a Model 5T. It can take a noisy sample, $6 at any time, and jump straight to the final clean image TAS, one shot.
How on earth do you train that? Seems like it would be wildly unstable.
The key is the consistency property. The idea is if you have a 0.6 on a true ODE trajectory, the final result, p-tax must be the same, no matter which 0.6 on that trajectory you started your one-step jump from. You enforce this during training, essentially forcing the model to learn the entire solution map to the origin. They use some tricks like special time schedules and weighting to make it stable.
And the consistency trajectory model, CTM, takes that even further.
CTM generalizes it. Instead of just learning the map to the origin, times 0, it learns the map between any 2 times $6.10, let's call it p size 2. It leverages a mathematical idea called the semi-group property, basically. Going from semi-developed to dollars is the same as going from semi-C to some intermediate time $4, and then from $2 to $1.
It learns the whole flow.
It learns the entire flow map. This means you can do generation in just a few steps, like 1 to 4, potentially improving quality over single-step CM jump, while still being blazingly fast compared to traditional solvers.
Wow. So we went from painstakingly tracing the path, DDPM, early solvers, to just training an AI that instantly knows the destination, CMCTM.
That's a great way to put it. It's a fundamental shift in approach.
Okay, last piece. Let's connect this back to some deeper theory. Optimal transport, OT. What's the basic question OT asks?
OT is about efficiency. Given 2 piles of stuff, probability distributions in our case, like a simple Gaussian noise pile and a complex image data pile, what's the cheapest way to move the stuff from the first pile to match the shape of the second pile? Cheapest usually means minimizing total distance moved.
And the paper connects diffusion models to this via something called Schrödinger bridges.
That's right. There's a deep mathematical link. A version of OT called entropy regularized optimal transport turns out to be equivalent to a stochastic control problem called the Schrödinger bridge problem, finding the optimal way to evolve one distribution into another over time, with some randomness.
So where do diffusion models fit in that picture? Are they optimal?
They are a specific case of the Schrödinger bridge. Specifically, they correspond to the zero control limit. It's like finding the bridge path when you're not actively steering or applying any control force, just letting diffusion do its thing. The math shows that the reverse equation you get in this zero control limit matches the reverse SDE that diffusion models learn.
But wait, if the goal is optimal transport, is the path followed by the standard PFOD solver actually the most efficient path? Does it achieve that minimal cost?
That's the crucial distinction. And the answer generally is no. The paper mentions specific results showing that the deterministic flow map generated by the PFODE is not necessarily the true optimal transport map, at least not for the standard quadratic called function people usually consider in OT.
So diffusion models are related to optimal transport. They solve a version of the Schrödinger bridge, but they aren't guaranteed to be the absolute most efficient way to transform noise into data.
Exactly. They find a path, a very useful one that we can learn and control, but it's likely not the theoretically cheapest path in the OT sense. That's an important theoretical caveat and an area for future work.
Okay, incredible. We've gone from these scattered ideas, variational autoencoder, score matching, through this powerful unifying theory based on continuous time dynamics,
which then unlocked these amazing advances in controlling the output with guidance like CFG, aligning it with DPO, and making generation almost instantaneous with things like DPM Solver v3 and consistency models. That unification was key.
We really do have tools now to make high-quality stuff incredibly fast and make it follow complex instructions or preferences.
The foundations are incredibly solid now.
So what's the provocative thought to leave people with? If speed and control are largely handled, where does the frontier move next?
I think it's about pushing the boundaries of that transport itself. We've gotten good at mapping simple noise like Gaussians to complex data. But what if we want to transport between more complex distributions? Can we take these fast methods like CTM, these learned flow maps, and not just make them fast, but make them provably optimal or near optimal in the OT sense,
even for really structured, non-Gaussian starting points. Ensuring the path we learn isn't just a path, but truly the best path. That feels like the next deep challenge.